So I am honored to introduce the 2016 Leslie C. Meyer Lecture to be given by Dr. Jurgen Spranger, the Meyer Senior Genetics Scholar here at GGC. The Meyer Senior Genetics Scholar position was created in 2010 to honor the legacy of Dr. Meyer, a longtime friend and supporter of GGC. During World War II, Dr. Meyer experiencing caring for soldiers who had lost limbs in combat provided the inspiration for his interest in caring for children with skeletal anomalies. He served Shriners Hospital for Children in Greenville as a surgeon and chief of staff for over 30 years, where he trained several generations of orthopedic surgeons. In 1954, he founded a school for children with disabilities, which later became the Meyer Center for Special Children. The Meyer Center continues to provide care, instruction, and services for children with physical and intellectual disabilities in the upstate of South Carolina. In 1976, Dr. Meyer invited GGC to begin holding genetics clinics at Shriners Hospital, an activity that has continued monthly for 40 years. He joined the GGC Board of Directors in 1995 and was named to the first class of Emeritus Directors in 2006. He was a treasured friend of GGC and of llamas everywhere. Dr. Spranger was selected to fill the Meyer Senior Genetics Scholar position because of his broad experience and recognized accomplishments in the area of skeletal genetics. Dr. Spranger is a former professor and chairman of Children's Hospital at the University of Mainz in Germany. He is an international authority on disorders of the skeleton, and author of the widely acclaimed text, Bone Dysplasias, an Atlas of Constitutional Disorders of Skeletal Development. In the time he spends each year at GGC, he provides indispensable consultation on patients with rare disorders, and he participates broadly in the center's educational programs. So it is my pleasure to welcome Dr. Jurgen Spranger to present the 2016 Meyer Lecture.
Shall I say? I've been coming to this place since about, since 98, every year. The book she just mentioned couldn't have been done without me being here because this is the only thing you want to do is fight. Anyway, that book wouldn't have been possible without coming here, because that's the only place where I can work from 9 to 4, or 9 to 5, 9 to 6, 9 to 3, if Russia wants to play tennis with me. Anyway, this is the only place where we can work. At home, you're diverted and so many emails and questions. Well, diversions, going to the coffee shop, etc. Anyway, this is what Roger asked me to do. Originally, he had a different topic. He asked me to bring you up to date to the most modern ways in 2016, and he was lenient enough to boil that down and ask me this simple question, and not original one. But anyway, as all my previous speakers have done, they have adhered to this rule. If you want to know the present, you have to know the past. You were reminded of Lejeune and other people. I go a little further back. Make a diagnosis. Now, you junior genetic advisors. What's the diagnosis of this one? My hearing is really has deteriorated. Well, my God, they knew it. I thought you might make the diagnosis from this one down here. These are all the genes, and I understand that some people these days look at the gene and they say, well, if it has a mutation, that gene must be a Meckel syndrome. Yes, it is indeed, it is Meckel syndrome. Now, who was Meckel? Here it is. That was 200 years ago. He was a pathologist. So, very well, developmental biology really was started by the pathologists. So you could say from 1800 to 1920, they defined the pathologic phenotypes as Meckel did. This was the original paper here. This description of two siblings were who he dissected, and they had very similar anomalies. And he described them. And why did he describe them? And this was the ingenuity of this guy. He described them because he said primary malformations, ursprüngliche Bildungswege, allow insight into the normal development. This is a brilliant idea. By studying malformations, the normal development is revealed. Remember, it was 200 years ago. So he's really the father of developmental pathology. I give you, focusing on skeletal disorders, I give you another older gentleman that was Kaufmann. He described this condition here, and these are his drawings. They didn't have photo. They had to draw it. That's his original drawing. Isn't that beautiful? To make a diagnosis. And how do we make a diagnosis? They just put the rating on it. That's what it is. Thanatophoric dysplasia. So he was the first to discuss. If you look at his book, I got his book. He had a marvelous other condition in there, which he also thought was the same condition, that it's orthopedic digital syndrome. You don't get it. Anyway, this was Kaufmann. And then the 20s to the 80s, and here is one of the geniuses who described the phenotypes in the living. First of all, the pathologist who described the phenotypes in the dead, and now it's this time here when we described it in the living. And this is his masterpiece. It's in the library. You have to look at it to see what he did. As far as the skeletal dysplasias are concerned, I wish to give tribute to my old friend Meyer, who died in 2008. He was the guy, the radiologist. He's a pure radiologist. His daughter had achondroplasia, and that explains why he got interested in this field. And he wrote this masterpiece. And what he did, he said, we have in childhood, since children develop as a fetus develop, we have to look at the newborn 5-year-old child. We have to have the whole age-dependent sequence, how a disorder develops from the newborn to the adult. It was a very good idea, and that we got together, I don't remember how, but I must have been in Baltimore anyway. So we got together and put this atlas together where we tried to adhere to his intent, to his insight. We have to look at the whole age range to understand these disorders. Now, this was history. Here's the question. What do you do when you see a bone in the flesh here? Must be a crooked bone. Yeah. Well, you get a radiograph, please. Now you have a radiograph. What's your next step? Get more radiographs. Get the other side. Is it unilateral or is it bilateral? Is it just the femoral? Or is it more than just the femoral? Oh, look at this. They look pretty normal, so it's just a femoral. You say femurs. It's not, it's femoral. Okay. And then you get more x-rays, and this is the minimum I am asking for when you ask me for a diagnosis. Get a pelvis, the radiograph, get a lateral spine, and get the hands. Most of the pictures I have to look at, or many of the pictures come from orthopods. They never did x-rays of the hand, because the hands are usually not what they are dealing with. But the hands have so many double bones, and so many epiphyses, and diaphyses, and metaphyses. This is just a wealth of information which you get from a hand, and very little irrigation to the child. Okay, so that's what you get. So there's this child again, whose crooked bone you just saw. You look at him, and then you find, is it syndromic or not? The main question here is intellectual visibility. Sometimes difficult, because it depends partially on the doctor. Does he see the aberrations or does he see it? If a guy does not see the minor abnormalities, then it's non-syndromic. So syndromic versus non-syndromic has to have a guy at the end of the diagnostic line who really knows how to differentiate an anomaly from a normal variant. Make it syndromic or not syndromic. And then you get a diagnostic idea and compare it to this child, and here it becomes difficult. Does this child have the same minor anomalies as that one? Look at the different, the mouth is different. Is it the same disorder or not? I'm afraid we cannot decide. Some of these children have mothers who are diabetics, so sometimes it's a diabetic disorder. So in the words of John Opitz, it must be a developmental field, which means that developmental abnormality that has multiple heterogeneous causes points to a developmental field and its defects. So I don't know whether this child has this disorder or not. I don't know of a gene that causes this disorder. One may be found. Some, of course, the maternal diabetes, most of them are not associated with maternal diabetes. But what you can say here, and now we get to what David said, a dysostosis is by definition, or we define it as such, a malformation. A malformation affects single organs, but not tissues. Meaning, single organs are affected, unilateral or bilaterally, but the rest studied. But the rest of the organs are normal. So it's localized, it's an abnormality of bone as an organ, abnormality of the femur, abnormality of the phalanx. But the other bones are normal. So this is a dysostosis because the other bones are normal. In contrast to dysplasia. This was not in your list, David. You have malformations and you have dysplasias. Dysplasias are disorders of bone as tissue. So all the sides that share a tissue characteristic are affected. Here you see all the metaphyses are abnormal. All the bones are affected in a very systemic way. So a dysplasia is the defect of bone as a tissue. And you can say the same about the skin. It is all of the defects. The entire skin, psoriasis, must be a dysplasia. A single anomaly like a hidden tumor may be a malformation, because the other tissue, well, the other vascular structures are okay. So this is a dysplasia. Again, you get a lateral spine, you get a hand, and you're happy to see the child also. So this is a dysplasia. This is pseudo-achondroplasia. Now here comes again. This is your picture. And there are malformations, disruptions. Disruptions are secondary malformations. Thalidomide produced malformations. But since the origin, the original plan of the organs of the affected child was normal, the child who was exposed to thalidomide had a normal origin, normal genes. Everything was normal. But then something happened. Thalidomide, vitamin K deficiency, something happens. And the same malformation results that becomes a disruption, or what we also call a secondary malformation. And then there are dysplasias that are normal from the very beginning. There are genes that are active at the beginning, but that affect all tissues. And then there are deformations, which David already outlined. But at one point, I also decided to normal variance. Never forget, when the patient is short, he may have a dysplasia. But he may also, what is short? When is a patient short? Well, we just say when he's in the first percentile. And we just say the 1 percentile is abnormal. That's not true. Because the shortest child in a crew of 100 is normal. One must be the shortest. He's the 1 percentile. Well, that's a normal variant. He's one. Never forget this when you see a crooked bone. It's just a normal variant. Look at the parents and think of the statistic. The shortest is the 1 percentile. 1 percentile means just that we scientists have agreed to say when something is in the first percentile or 5th percentile, there may be a reason that this is not normal, and we advance the hypothesis that it may be abnormal and we search for pathologies. But never forget 1% of the shortest children are normal. Anyway, so that's a normal. Next one shows essentially the same thing. A malformation results from a temporarily limited gene expression. The gene interferes in blastogenesis with organogenesis, but then many of those genes are just active in blastogenesis, are then just turned off. But in the dysplasias, the gene is abnormal and continues to be abnormal throughout life. It may manifest before birth. These are then the congenitally manifesting bone dysplasias, like achondroplasias, and others may only manifest later. And then there are a group of disorders that combine both dysostotic and dysplastic characteristics. Okay, now we go in the 1980s, Roger's primary challenge. What's new? This is new. They show you x-rays. You get an idea or two, but not many of the ideas. So what they do is just really hard. This example is true. This happened a couple of weeks ago. So, all of that was negative. What's the next step? Well, we go to whole exome screening. And that's pending in this case, and hopefully it will come out. So this is part of modern genetics, medical genetics. This is another example. Here is a guy with these symptoms up there, developmental delay, etc., etc. Mild anemia, well-nourished diet. Well, you don't think what it could be, you just too targeted sequencing, and it turns out this gene is abnormal, TBAX1, and that is associated with skeletal dysplasia. You look at the very well, and then you get the radiographs, more radiographs of this patient you make to kind of combine the molecular finding with the clinical phenotype. You look at the books and look at other children with this phenotype. Now, when you looked at this bone, we thought it was pretty normal. Maybe the cortices are a little thickened, not very much, but that is normal variation in thickness of the cortical bone. So you were not sure. And when you compare it to known cases, they have much more diaphyseal involvement, and that's the reason that this condition was called diaphyseal hemato, because they have abnormal blood values, hematodiaphyseal dysplasia. Now what you learn from this look first, screen first, see then approach has the advantage that we learn about conditions. We did not know the variability of this disorder. And only by whole exome screening and looking at the gene first, we found out that this almost normal bone is part of the spectrum of variability of this disorder. So it has to, it's a new way of doing things, screen first, look then. We still prefer the old-fashioned way. It's more sporty. Here's another one. I showed this to Roger some days ago. What is this? You see here, this patient has an extra bone here. Bilaterally. What is it? Oh, you do it the old-fashioned way to go all these differences of what it could be in order to really do a second screening, ask, check for this gene. Well, unfortunately, this child, in addition to have this extra bone, has something else. Look at this here. He has fusion of the dorsal portions of his cervical vertebrae. And then you go in the literature and look what you find. You find a paper by Dr. Roger Stevenson. And look at this, what he had. He had the other Katamanskis, at least the ones I looked up, didn't have this fusion. Roger's patients had it. You see, this segmental signs here, and the abnormal fusions. So this patient and Roger's patients are the same. Now, we have to do, I can't tell you what we know the gene, so Roger's got to get these patients now in to do, or look for cells, you may have cells, and to look if this child indeed has the Katamanska, or if this is a different disorder that combines the hand changes with the changes in the cervical spine. So this is fun combining medical genetics, molecular genetics with clinical genetics. Now, but the real exciting thing I feel is what the last years have all brought about. We do not know only about the phenotype described by pathologists and matricists of this world. We don't know only about the formal genesis, the dominant, the recessive, but we understand the pathogenic mechanisms. And this is what makes it really exciting. The pathogenic mechanism. What does the gene do to the proteins? What proteins are involved? What's the network? And we find then abnormalities of structure, proteins, we find abnormal metabolic pathways, abnormal silicon pathways, etc., etc. That is, we understand what the mutated gene really is doing from the mutation to the phenotype. And I'll give you a few examples of what we have learned. It's getting too much. Roger has put me at the end because he has unlimited time. You may start yawning and you may start closing your eyes. And when I see more than 30% yawning, I'll just stop. And some of the slides are complicated. My wife admonished me this morning, just be slow. Think of Obama. Think of him. Just make long pauses, and you'll be important. That's not quite what she said, but that's what she said. All right, osteogenesis imperfecta is known to all of you, and you all remember faintly that there are several types which differ in severity, in expression, and manifestation. And all of those 4 types that you see here are caused by mutations in type 1 collagen. The differences are phenotypic. There is a certain molecular gene phenotype correlation, but not much. There's another type that's a little bit different, very severe, almost lethal. It's also, well, if it's lethal, wasn't president, but anyway, in contrast to these other genes these other types are mutated here in the helical portion of the type 1 collagen, and this disorder is located in, or is caused by mutations in the propeptide, which is not yet intertwined. There is one other dominant form of osteogenesis imperfecta, which we have learned here, and don't ask me what I-FITM5 means. It's autosomal dominant. It has, I don't recall how they make up these names. Anyway, this is a gene that interferes with cellular, or that acts on cellular differentiation, and it's mutated. A form of osteogenesis imperfecta can occur, which is characterized by one nice diagnostic sign. This one here is hyperostosis of the radius, between the radius and the ulna. There is new bone growing out here, and those 2 bones may fuse during development of this disorder. This is a rare instance where you can make a diagnosis from a single sign. And you see bones that fracture, osteogenesis imperfecta, and have this lining here, that it's type 5, and it's IFITM5 mutation. Now, what we also have learned, this structure here, this helix, or the type 1 collagen, is formed from the right to the left. First, this part is formed, and then the helical portion is formed. So the formation proceeds from here to there. Now, we know there are quite a few forms of autosomal recessive osteogenesis imperfecta, and they all affect genes that are involved in the processing of the pro-collagen, that is, of the non-helical part of the type 1 collagen. And they are recessive. So when you counsel osteogenesis imperfecta, COL1 is a good first step to do, because 90% are caused by mutations of the type 1 collagen. But then there may be others that are autosomal recessive, and there are quite a few of them. And we know the function of many of these genes, what they do here in the processing of the pro-collagen. So that we have learned in the last years. Another example of structural anomalies. Talking about structural anomalies, I mean that the primary tissue is abnormal. The structure of the matrix is abnormal. Just talked about type 1 collagen. Here is another structure. Is fibrillin. Fibrillin fibers associated to become microfibrils, and we know that mutations in the gene that codes for fibrillin can lead to all of these conditions. They always are associated with tall stature. Now there are some that are associated with short stature, and we know that Chimeric Dysplasia and Weimar-Chiari syndrome. I'll show you Chimeric Dysplasia. Here they are. They're in the microfibrils, but fibrillin is mutated, the microfibrils are normal, and this condition, Chimeric Dysplasia, will result. They're short, they have abnormal hands and feet, not very much in the rest of the skeleton, and they have this lovely phenotype. It's just nice. It's dominant. Now there are other nice people. We look very, very similar, but this is a recessive condition. We called it years ago geriophysic. Gerios is Greek and means happy, funny. They have these happy faces. So how is it possible? And they have about almost the same acral changes. The hand, all of this is very, very similar. How can a dominant and a recessive condition lead to the same, almost same phenotype? Well, there must be something that interferes with the microfibrils. And indeed, this is so. It's getting a little bit more difficult. Here is TGF-beta. TGF-beta is bound to latent TGF-beta binding protein. And there is a substance that interferes with the formation of this binding protein. And this has the same final phenotypic effect as the mutation of the fibrillin itself. So TGF-beta binds to this site here of the fibrillin. If there's a mutation in the fibrillin, it cannot bind. So there's a rise of TGF-beta in the blood, in the tissues. And the same happens, the same rise of TGF-beta in tissues arises when you have a mutation in the ADAM-TLS2, because ADAM-TSL2 is involved in function. Now, what would you expect if a gene would mutate it that codes for LTB3? Should have the same phenotype. And it does. Here's the LTB3 gene coding for LTB3, and if we find a mutation here, a phenotype arises that's kind of the same or intermediate between the two. That's exactly what you expect. Now, if ADAM-TSL2 interferes with this fibril production, you would expect other atoms also to have an effect. Yes. The Weimar-Chiari phenotype may result, which is different from the Weimar-Chiari syndrome. Dysplasia caused by mutations in FBA1. there is an autosomal recessive variety and autosomal dominant variety of the Weill-Marchesani syndrome, and the autosomal recessive variety is called also ADAM-TS mutation. That then has a common pathogenic pathway, which is elevated TGF-beta, and the elevated TGF-beta activates one of the SNAD SMAD genes, and there is another disorder caused by mutations at the very end of this pathogenic chain, which is called, this is the Meyer syndrome. Anyway, then in this genetic mechanism pathway, we have 4 disorders, and now they resemble very much each other. They're all short, all have connective tissue abnormalities, resemble each other, but we understand they're common and they're different pathogenesis. I think this is a good story. You know this story. Common pathogenic pathway degradation of acid glycosaminoglycans. Wherever there is the breakdown of glycosaminoglycan heparan sulfate, and wherever there is a mutation in this metabolic pathway, disorder will result. It looks very similar, not identical, but if the mutation is here or there, the basic phenotype resembles. So we have called these different disorders families of disorders because they are pathogenetically related by a common metabolic pathway. So this is another example where we understand the pathogenesis. We have recently found a different pathogenic pathway, the so-called leukoropathies. Here is a core protein to which the acid glycosaminoglycans have to be attached by a strand of oligosaccharides, serine, xylose, galactose, glucuronic acid. There are enzymes coding for this metabolic pathway, attaching xylose to serine, attaching galactose to xylose, etc., etc. This region here, going from here to there, then to attach to chondroin sulfate or heparan sulfate, that is the mucopolysaccharide, has been called the linker region. And any of the genes involved in this metabolic pathway leads to a different disorder, which, however, resembles the disorder next to it, as in the mucopolysaccharide genes. They all have a skeletal dysplasia, many of them have skin involvement, some have other connective tissues involved, and here are the patients. Many of them have one common factor, is called congenital dislocations of the joints. Joint dislocations are shared by many of them. Marked scoliosis, etc. These are the different types that can form a family. Now, if you form a glycoprotein, which is needed in the matrix, you attach the core protein, you attach the carbohydrate to the core protein. But the carbohydrate, then becomes a little bit more complicated and interesting, has to be sulfated. So we expect that sulfation disorders will also cause similar phenotypes. Yes, it does. This is the sulfation pathway. This is the cell membrane here. Here you need a transporter protein that transports sulfate into the cell. There is a protein needed, an enzyme needed, a synthase that attaches sulfate to this phosphate adenosine phosphate compound, etc., etc. Now you will expect similar disorders to those you have seen here from abnormalities in the sulfation process. This is exactly what happens. Here you have one disorder that looks a little bit, resembles a little bit the Katalmansky you just saw. There's the next disorder, Osteogenesis Imperfecta, etc., caused by defects here in the transporter protein. Then there is a disorder here, SEMD Pakistani type, a brachioma caused by a synthase defect, and there is a disorder caused by abnormalities in this carbohydrate, so transfer and synthase. They all sample to a certain extent to each other, and they form a large group of disorders that are pathogenetically related. And this is just, this is 2006, so this is what I did one almost last one. The enzymes that are needed to link the protein are built in the endoplasmic reticulum. Here they are. In order to combine the core protein with the carbohydrates, they have to be transported into the Golgi apparatus. There it happens. Now, if the Golgi apparatus is defective, doesn't work, if these layers don't stick together, these enzymes, proteins, cannot be transported from here, the endoplasmic reticulum, to the Golgi apparatus. What you see is here, this is a normal, and this is an abnormal endoplasmic reticulum caused by mutations in TRP11. If this gene is mutated, the Golgi apparatus kind of disrupts. The proteins cannot be transported from the endoplasmic reticulum to the Golgi apparatus. They stay in the endoplasmic reticulum. That's what you see here. The endoplasmic reticulum kind fills up, there's a thing here it fills up with the proteins that cannot be transported from here to here. And this mutation then will result in achondrogenesis, this severe lethal condition. What we have learned, and it's not yet published, it has been presented at a conference, is that this condition, Skeletal Dysplasia, is caused by mutations of the same gene, different mutations, different phenotype, different development. These patients are severely affected but survive. That's the last example I'll give you. There are microtubules that are formed out of tubulin. Tubulin strands are put together and form microtubules. The microtubules again associated to become cilia. We all have cilia working at this moment by removing mucus from our bronchi. These are mobile cilia. But there are more other cilia that are primary, non-motile, sensory, that are responsible for transporting structures through the cell. This is a microtubule. It combined to become cilia. And there are a lot of proteins that are needed to form the microtubules, to form the cilia, to transport the substance on the surface of the microtubules, etc., etc. And there are quite a few genes, there are many genes known, that affect Genes are mutated that affect protein structures associated with cilia or involved in the production and degradation of cilia. Cilia, this is exactly what a cilium, and we know about genes that are mutated and that cause quite a variety of neonatal conditions, including one that's seen here that's compatible with survival to adulthood. They all share one phenomenon. They all have very narrow thoraces. So these are ciliopathies. There are different ciliopathies, and more ciliopathies, the same ciliopathy phenotype can cause by different mutations in a lot of different genes. So this is another family. I think now I see no yawning and tired eyes, which is perfectly all right, and it's all Roger's fault. He did not set a limit to what I'm saying. And as a Meyer professor, I'm entitled to do that. But this is the last chapter. You have a patient with a diagnosis. I think that courtesy is everything. And I'm afraid it's a remark at the end of my talk. Can is he in a position to speak up?
Yes.
Can you make a diagnosis? What is it, Curtis? Look at this. You see the metaphyseal change, very little bone here, osteopenia. Huh? Well, you have to make a diagnosis because you can treat this patient. You have to treat him. He may die. It's hyperphosphatasia. And this is what you're going to do to him. You give him alpha-tase, and the bones will improve. The child will stay alive. In a mild form, hyperphosphatasia may be present in an older child or an adult, but they have bone pain. And you give them alpha-tase, the pain disappears, and this child stays alive. Huh? He's asking for the price. The first year, it's $1 million. And then arises, well, that arises question. If it's the first year, 1 million, it's always milligrams per kilogram. There will be 2 million in the second year, and I don't know how much. I mean, the company sponsors it to this moment. So a few patients have been treated. So, but this raises some ethical questions which we'll not discuss today, where these bills come from, and this kind of paper. Or can you deny it to that patient? The patient will die. But this is the only example where I have a clear-cut effect from replacement of a missing or defective protein. Here are other examples. We substitute enzymes, we give biphosphonates, we transplant. These are all therapies that affect, well, therapies that are not tertiary which are secondary or well, they are not primary. Primary therapies would change the basic defect, would change the gene. Secondary therapies are dealing with the manifestations of a disorder, by interrupting the pathogenic mechanism. And tertiary therapies then deal with the phenomenon that have not been prevented to appear. These are the ones that affect the pathogenesis. None of them are really satisfactory. That includes eye cell disease. That includes all of the mucopolysaccharidoses. They do little on the brain development in the mucopolysaccharidoses. They do nothing on bone growth. They are provided, but they're not what we see in hyperphosphatasia or what we would like to see in many other disorders. There is little effect of the fracture rate in osteogenesis imperfecta. They all get biphosphonates. Biphosphonates impede action of the osteoclasts, that they impede bone breakdown, but they don't have further bone growth. The effects are unsatisfactory. So what do we do in a patient anyway? And I just want to remind you, I have this patient, and Kathy just told me she has to make the diagnosis, and this patient you should never do a diagnosis from a single film or a single sign. Anyway, but this is a characteristic sign. This patient has achondroplasia. So we don't have therapy for achondroplasia at present. So we do all this at different times. At 6, we examine the child. At 2 years, we do a hearing test. We start with physiotherapy and all the dealings you offer daily on a daily basis. This is what we do with most of the patients. And it's satisfying to help the patient this way. We make them even grow by cutting their bones and lengthening their bones. This guy was supposed to be 130 centimeters tall. He's now 150. I met him recently. He's not a happy person. Would you think by changing your size, if you must be the shortest one here. Patients with Turner syndrome are always short. To a certain degree, if you can lengthen, that doesn't make them happy. Obviously, will the patient be happier when you do what we want you to do? I had siblings with high cartilage hyperplasia. We lengthened the guy and let the girl, because she didn't want it. The guy killed himself. The girl lived to her natural end. Why is that so? Well, if you approach the normal, you really do want to know. If you are clearly too short, you decide to lead a different life. You're different. And you accept and you become proud of being different. And then doctors come to look at your trouble. And then they are no longer different, have no different, but they compare themselves continuously to. So whenever you do something, ask yourself what's good for the patient by projecting yourself into the patient. I end this talk now because achondroplasia is the most common form of dysplasia. And we know the pathogenesis. It is by a receptive defect that interferes so that there's a constant impediment of cellular growth here by impeding this cell-promoting, growth-promoting P21, which in excessive amounts leads to cancer. So we know that. Mutations in this gene cause a whole family of disorders. Differing other mutations is another reason for creating bone dysplasia families. But they all are caused by defects in the receptor here. Defects in the receptor lead to continuous inhibition of P21. Now, what could you do? Could you perhaps interfere here? If you interfered here, then this continuous inhibition would be in itself blocked. Yes, This is what people try. The mutation leads to normally the attachment of the fibroblast growth factor leads to a dimerization of these two structures here. And since it is mutated, they cannot be dimerized. So there is a protein, a short protein here that imitates this dimerization process and then blocks this inhibition so that cells can grow. So inhibition is inhibited. That works in mice, but doesn't have been tried in men. But there is a different pathway here. There is CNP, and CNP also blocks this growth inhibiting gene. Now, this is a possibility to create and they have been creating CNP analogs. They work in mice, and they are now in a phase 2 study with children. 10 children got 15 micrograms a day, and they had an advanced growth velocity, which does not mean anything for the pharmacology. They just may grow faster, but end up earlier. So this is not good. Anyway, there is an approach, and hopefully it will turn out to be positive. So that's a fast one. Achondroplasia maybe will become treatable. Osteogenesis imperfecta, anti-rankles, antibodies will be tried. Other forms to treat idiopathic osteoporosis and other. Numerous skeletal dysplasias may be treatable by this process, which is said to alleviate antidepressant, particularly stress. This is our hypothesis. And then there comes a final line on which I will not talk. Thank you.